Hey guys, so today we're going to talk about the combined gas law. So where does the combined gas law come from? It comes from combining Boyle's law, Charles' law, and Gay-Lussac's law. So the equation for the combined gas law is P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. But as you can see, I've kind of circled everything that incorporates Boyle's law in purple. So P1 times V1 is equal to P2 times V2. We saw that in the other video. Charles' law is outlined in blue, right? So V1 divided by T1 is equal to V2 divided by T2. And then Gay-Lussac's law I circled in red. Pressure divided by temperature is equal to pressure divided by temperature. Remember, anytime we're dealing with temperature, it is always in Kelvin, guys. Temperature, is always in Kelvin. All right, so question number one is if we have a sample of helium in a 100 milliliter container at a pressure of 77.7 kilopascals kPa, if that helium is transferred to a 250 milliliter container, what is the new pressure if the temperature changes from 20 degrees Celsius to 15 degrees Celsius? So we're going to go through, and we know the combined gas law math equation is P1 V1 times T2. We just cross multiply here to get this value here, right? Is equal to P2 V2 times T1. We divide out V2 and T1 to isolate P2 because the question is asking for the new pressure P2. Okay. So we go through we were given pressure 1 of 77.7 kilopascals. We were given temperature 1 of 20 degrees Celsius. Remember, we have to convert that to Kelvin. So we add the 273. That's where we get 293 from. And our volume 1 was the initial 100 milliliters. Our temperature 2, the temperature that we changed to, was 15 degrees Celsius. Again, we convert to Kelvin. Add the 273, we get 288. And the volume changed from the 100 milliliters to 250 milliliters. Okay. So once we've isolated our variable, we can plug in our values and we can crunch some numbers. So when we take the 77.7 times 100 times 288, we get 2,276,610. We divide that by 250 times 293. When we multiply those two values together, we get 72,000. So 2,276,610 divided by 72,000 gives us a value of 31.62. My units have canceled out to provide the unit of kPa. All right, question number two. A gas heated to 80 degrees Celsius has a pressure of 180 kilopascals kPa. If the container expands to hold a volume of 800 milliliters, what was the volume of the gas at a temperature of 50 degrees Celsius and a pressure of only 120 kilopascals? So again, we're isolating V1 when we read through this, right? So we were given P1 as 120 because it asked what was the volume when it started with the pressure here of 120. That tells me that it's P1. T1 in this case is 50 degrees Celsius. Okay, so we convert that to Kelvin. Pressure 2 is after it was heated, we end up with pressure 2. 180 kPa, temperature 2, again we convert to Kelvin, 353 Kelvin. Okay, volume 2 was 800, so it expanded to a volume of 800 milliliters. Okay, so the verbiage in this question kind of is a little tricky, and you'll see that when we get to the end, unless you're really adept at reading the note on the board. But we work through our given, right? We isolate V1 here. Okay, we divide out P1 and T2 on both sides. And so that gives me V1 is equal to, and I crunch my numbers here, 180 kPa times 800 milliliters times 323 Kelvin. Divide that by 120 times 353. We end up with like 46,512 divided by 42,360. And when we divide those two numbers together, we get 1,098.75 milliliters. So this is where the verbiage is a little tricky. It says that the volume expands to 800 milliliters, but my answer is larger than 800 milliliters. So what this tells me is that when I'm dealing with the pressure side of things, the pressure affects the volume more than the temperature does. So we're calculating based on temperature, but the pressure keeps it at 800 milliliters, if that makes sense. So we initially started 1,000, so it's bigger than the container could possibly hold, so the pressure squishes it down to 800 mils. Alright, so question 3. A cylindrical coffee can is welded shut and then allowed to cool to 20 degrees Celsius at sea level, which is approximately 1 atmosphere. The height of the can is 20 centimeters, the radius is 15 centimeters. So if the bursting pressure of the can is 3.75 atmospheres, to what temperature may the can be heated before it bursts? So one cool fact about this question is we can kind of assume that the volume is going to remain the same. The can is just going to rupture. Okay, so volume tends to just kind of cancel out in this case. So that makes the math a little bit easier for this question. All right, so we are given P1. Pressure 1 is 1 atm. This is what happened at the beginning, right? It was welded shut. We have T1. T1 is 20 Celsius at sea level, right? So we were given V1. I'm going to forego doing the math on that because it's not really needed. So we just make V1 equal to V2, V2 equal to V1. That allows them to cancel each other out, okay? But my pressure 2 is the pressure at which the can ruptures. That ruptures at 3.75 atmospheres, okay? So we're going to calculate T2, canceling out the volume along the way. So T2, when we isolate T2 up here, we divide out P1 and V1 on this side. What we do to one side, we do to the other, so we divide out on this side. We end up with 3.75 atm times my 1 liter, okay, for my volume, times my temperature of 293 Kelvin, divided by my 1 atmosphere from my sea level, that's where that comes from, right? Divided by the 1 liter that the can is, okay, so those are going to end up dividing out, right? When we multiply 3.75 times 293, I end up with 1098.75 Kelvin. So when we heat up that can, we have to really, really get it hot before it finally just